All right, DC generator operating principles. Before we actually get into this learning task, we have to go over a couple of just small reviews, some left-hand rules that are going to come out of your first year material. You would have learned this stuff back in first year, but it's third year by now, so there's a good chance that you may have forgotten some of these. So we're just going to go over all of the left-hand rules relatively quickly. First one that we're going to take a look at is going to be my left-hand rule for conductors. That's going to be this bottom one over here, which states that if I know the direction of the current that is flowing through the conductor, if my electrons are actually moving in that direction, what I can do is I can put my thumb in the direction of the current, and then I can go and wrap my fingers around the conductor. And the direction that my fingers wrap around the conductor are going to go and tell me the direction of the magnetic field, how it's going to be rotating around there. We are going to go and have a magnetic field that is going to be a complete loop, because magnetic lines of flux do form complete loops, but it is going to be continuously rotating in that direction around it based upon the direction of current that we have going through the conductor. That's the first one that we're going to go and have. The other one that we're going to have is going to be our left-hand rule for coils. And the left-hand rule for coils is where I've got a bunch of wires that are now coiled together, what we see over here, and I'm going to go and wrap my fingers around here in the direction of current going through those coils. So if the current is going like this through those coils, across the front, like that through these, I'm going to wrap my fingers around, as shown over here, and then my thumb is going to go and show me where the north pole is going to go and be. It gives me that polarity of the actual coil. It's taking this and it's just combining it together so that I can go and figure out my overall magnetic lines of flux that are going to be going through here. Going from the north, they leave from the north, they go back to the south at the far end like that. Those are going to be two of my left-hand rules. The other one that you should know is going to go and be this one, which is Fleming's left-hand generator rule. First of all, make sure you're doing all of these with your left hand. I cannot tell you the number of times where I've seen students just using their right hand, because most of you are right-handed and you're more used to it, and so students will just try to do analysis using the wrong hand. Know what your left is, what your right is, be careful when you're doing it. When we're looking at this is a generator rule, and because it is a generator rule, we are looking for generated voltage and generated current, which means that we're going to go and have to have a couple of things that are going to be already existing. EG is equal to BLV. We're going to go and generate our voltage by looking at the flux density, the length of conductor that's going to be active inside there, and the velocity of whatever we have pushing our conductor through or pushing our field past. Those three are what we're looking for to go and get this, which is going to be voltage, and voltage creates current. So what we want to do is we want to go and ignore the middle finger for now, okay? Start with the finger gun, just a thumb and a finger, and establish those two in relationship to whatever the circuit is going to go and be, the motion of the conductor in relationship to the field. We're going to go and call this thing the thrust, and we like the term thrust because it lines up with thumb. Okay, so it says thump. I can write that better, thumb, like that. So thumb is going to be thrust. First finger, it's called the index or pointer, but we're going to call this thing first, is going to go and be field. The magnetic field, we're going to point this in the direction of field going from north to south. Okay, is what we need to do. Once we have gone and figured out where our thrust is on our conductor and moved our thumb, so it's going in the motion of our conductor through the field, and we've got the north to the south, then what we can do is we can unfold our middle finger. Okay, don't start with that middle finger out, just start with the finger gun. Once you have got these two established, then you can go and take a look at this, because this is now going to be the result. Same as in this relationship up top over here in the equation, we need the flux and we need the velocity. That's going to be motion, and flux is going to be my first finger. We need those established before we can go and get the value of voltage. Same thing for this. This is then going to tell you the direction that the electrons are moving through any sort of a wire. Okay. With those three rules, and like I said, these are not inside of this module. They are coming back to you from first year materials over here. We can now move on into our generators. We're going to have a bunch of stuff satisfied in order to go and run a generator. One of the first things that we need to do is that same formula that we were just talking about, EG is equal to BLV. We need to go to create voltage. We need to have velocity. That's going to be provided by my prime mover. which is going to be the engine or whatever we've got attached to it. We're going to have length, which is going to be conductors themselves, wound, lap, wave, frog leg windings, all of those things. And we need to go and have flux density, which is going to be magnetic flux density on here. And so what we're going to look at right now is going to be 3 different methods that we have for creating magnetic flux density. Those 3 main ways to go and create flux are going to go and be me to go and use either permanent magnets, which is going to be one way where I'm just going to go and have actual ceramic magnets, permanent magnets. Or I'm going to go and have electromagnetic field poles. We know that if we take coils of wire and we run current through them, we know that we can go and create magnetic poles. What we see up top over here, we can create a north and a south based upon the direction of current that is going to be going through that. So we're going to go and have 3 main types of field poles that are going to go and provide the flux that we're looking for inside of this. And they're going to be our permanent magnets, and then we're going to go and have series field coils, as well as we are going to go and have shunt, and they're going to be kind of a parallel type of field coil that we're going to go and have. Let's start by talking about the permanent magnet ones. We don't have an illustration of permanent magnet one, but it would be basically the same thing as what we see in this drawing over here, only that this section would be a permanent ceramic magnet, and this section would be a permanent ceramic magnet. We cannot get the flux density out of these that we would normally be able to get out of electromagnetic ones, so they're not commonly going to be used for large-scale DC generation. We'll use them for small scale, if I need to go and just create a little bit of voltage for something, generally running off of a larger prime mover. They give you, the example of ignition circuits on an engine where you're going to have to go and create a little bit of voltage that you're then going to go and collapse across an inductor, to go and get your spark and things like that. But they're going to be relatively small components that we would use for these. They're also known as magnetos because they use that permanent magnet. If I'm going to go with an electromagnetic field pole, I have got 2 main types that are going to be there. I've got 2 main connections, which are my series and my shunt. And that series and shunt, I can choose how I'm going to go and feed that. Do I want to feed them from the generator? If I feed them from the generator, it's going to be called self-excited type of generation, where the generator creates the excitation. Or if I want to feed them from a separate source, then it's going to be called separately excited. So I select one of those. Do I feed these things from the generator, or do I do them from, I can't spell separately here while I'm talking, but separately excited, there we are. We choose whether we want these 2 things to be fed from the generator or whether we want to feed them from outside the generator, and then we choose what the connection is going to go and be. Series, or if it's going to go and be shunt. Okay, so let's go and talk about now the actual self-excited series field winding, which is what our illustration shows over here. Our series field winding is going to go and have a connection that is going to be in series with the armature. Now, we talked about the armature yesterday. The armature is going to be that rotating section of a generator that is going to go and be where we're going to pull our voltage off. It does have our commutator and our brushes on it, and it's going to be made up of windings of wire that are going to be inside of it. Okay, the windings of wire inside here, this is where we're going to go and have our wave and our lap and our frog leg, and all those other ones are going to be on this armature that they're showing us right now, which are then going to be connected to this commutator. And then that commutator is going to go and have leads that are going to go and come off of it at the brushes, which are going to be those carbon things that ride along the outside, the carbon graphite. That's all going to be where I'm going to be creating voltage from. So I'm going to go and have rotation over here. Point that out. I've got rotation over here, and I'm going to go and rotate this thing inside of a field. And as I rotate it inside of a field, I'm going to go and get generated values of voltage that I'm going to be able to go and take off of this and feed out to my external load. My series windings are going to go and run through in the same direction. I'm going to go and have current. If I follow this through, I'm going to have current that is going to go from negative to positive through my load, but through a source, and a generator is a source, it is going to go from positive to negative. So we're going to go through this thing as a source. It's going to go through my armature, so it's going to go through those windings in the armature, come back out the other side of the brushes, and then my current is going to go through, goes across the other side where it's going to be windings in the same direction, and then back down and through to here. Use your left-hand rule. You can go and curl your fingers around in the direction of current flow on each of these. You can establish those poles. We can see the current is going through like that. We can see the current is going through like that. If I use my left-hand rule over here on the right-hand side, I see that my left-hand rule for coils makes this the north, which would mean this would have to automatically be the south. And then on this one over here, this one, my left-hand rule is the north. This one would be the south. Ultimately, our entire motor is going to be mounted on a frame. And what the frame does is it not only provides a place for the motor generator to mount, it also provides a path for magnetic flux, because magnetic flux needs to form complete lines going from north to south. We are going to have magnetic flux lines that are going to shoot across this gap over here. We're going to take a look at them later on. As they shoot across that gap, then they're going to go and enter and drive through the inside of this. Once they come to the far side of that field pole, then they will go and travel around through my casing and back to this side here, where they're once again going to go and fire out to the other side. So what you see is you've got this continuous path for magnetic flux that's going to be created by my field poles and by the actual casing of this thing, the stator, the stationary position. We do want those stators to be magnetic. Now, you will get aluminum or stainless steel motors and generators that are going to go and be out there. It doesn't matter whether we're looking at a motor or a generator, the construction is going to be the same, even if we have got an aluminum body or if we've got a stainless steel body. Inside of that outer casing, there will always be a ferrous plate that's going to be wrapped around the inside of the stainless steel to go and provide you with that complete path for current flow. In some cases, they'll even just go and continue the laminations all the way across. Because this winding that we have, the series, is connected in series with the armature, whatever I deliver out to the load, that full value of current out to the load has to come back, there's my load, through the armature and then through these. So these are going to have to be large gauge, large AWG, wires that we are going to go and have. Because they're going to go and be large gauge, and because they're carrying lots of current, we don't need to have a lot of turns. It's going to be relatively few turns that we are going to go and use for these, because their gauge is so large and because they're carrying such a large amount of current through them. Therefore, they're going to have a stronger magnetic field just off the get-go because they have so much current going through. My shunt field for a self-excited generator is going to go and look like this. I want to just follow two paths through here. The first one is just going to be my generation path, where I'm going to go and have from my load traveling back through my generator. Remember, my generator is a source. It's going to go from positive through my armature, back out the commutator, and then down out through here. So this is going to be my main generation path over here. That's what I'm delivering out to the load itself. What I'm also going to go and have is I'm going to go and have a second path that comes off here. Note that we have got this connection over here from our main path that I'm then going to be able to go through each of these, and then through this field rheostat and back to here. If I were to trace this, you'd see that this would be a complete loop looking like that. That complete loop that we're looking at over there is going to go and be my shunt field windings. These are going to be placed in parallel to the armature, and they're actually going to be a load on here, which means that the current is going to flow through them from negative to positive. We can look at that stuff later on when we go into the types of generators as we're going to cover these. But they are going to be getting power delivered from that shunt field. As it goes through there, once again, it is going to go and create my, I'm just going to erase a bunch of these. It is going to go and create my field poles, because if I take a look, here's my current traveling through like that. Use your left-hand rule on there, and then this side over here, same deal. Curl your left hand around that coil, and you see that we are going to have our north here, which is going to send us a line of flux across to the south. The south is going to go across to the north here, and then it's going to go around the outside of our generator back to this one over here, and it completes that path that we would need for flux. Because it is operating in parallel, it does not need to go and carry all of my main current, right? This is my main current path that I'm going to go and have over here. Because it's not carrying all of that, we can get away with smaller turns of wire, smaller, finer wire, so it's going to be smaller AWG. And I'm just going to go with a lot more turns of it. You know, a tiny amount of current but I'm going to have many turns of it, which means that I'm going to go and get my flux. I don't know if you guys remember the formula for flux, but flux is determined off of ampere turns. That's what it's called. So I can go and have either a high amount of turns, which I have over here, and a small amount of amps, which I'm going to go and have over here inside of the shunt one, and I'm going to still go and get my flux out of this thing. Or if I go back to the series one over here, my ampere turns is the same formula. Ampere turns is going to go and give me my flux. If I take a look at this one, I'm going to have a large amount of amps, but a small amount of turns. Either way, we see that we can go and get a large amount of flux from the series or from, in this case, the shunt or the parallel winding that we see. We do have another component over here, which is going to be a field rheostat. This is not a potentiometer because it's got one end connected in common. We're not using it to sample voltage. We are using it to go and create varying values of resistance. What I can do is I can use this rheostat to go and adjust the amount of current that is going to be going through this shunt circuit over here, which means that if I adjust that current, I can adjust the amount of flux that I'm going to go and have out of here. If I go and decrease the resistance, so R goes down, my amps inside of the shunt are going to go up. If the amps go up, my flux inside of that is going to go up. And if my flux goes up, according to EG is equal to BLV, what I'm going to be able to do then, if the flux is going up, my voltage output on this generator is also then going to be able to go up. And if I reverse the resistance, go in the opposite direction, all the opposites would go and happen. If my resistance were to go up, my amps would go down, which would mean my flux would go down, which would mean that my volts would go down. What we see is this becomes a control for the output amount of voltage. I don't have to try to control how fast this is rotating, which is a good thing because engines are hard to control the RPMs accurately. It's much easier for me to go control the current that I'm going to go and have through for my ampere turns. Okay, that's my shunt winding. What we can do if we want to go and get the best of both worlds is we can go and have series and shunt windings on these. The series and shunt windings together are often going to be called a compound type of winding. If we take a look at this drawing that we have over here, I'm just going to move this one over here. It's a bit of a complicated drawing. There's multiple paths. We're going to start with our armature, which is where we are generating the voltage itself. Okay. So my armature is going to go and be where I am creating values of voltage that are going to go and get sent out to my load. So I'm going to go through my armature. I'm going to go and follow a couple of paths through. First one here is going to be my series path, where I'm going to go and be able to carry this through here, back out to here, which is going to be able to go out to the load on that side, as well as I'm going to be able to carry from here to there. So I see that I've got a generation path, that green path that's highlighted over there, that is going to go and carry current out to my load through this series winding. What I've also got on here is going to be another path where I'm going to be able to now go and take from my generator. I'm going to go and highlight this one as a blue path. This blue path over here would be running in on the same one here, but then where I come and generate out of here, instead of going through the series, I can go through a diverter rheostat, which is going to be a larger value of rheostat, which is then going to allow me to go and divert some of my current and send it back out. It's kind of a confusing looking path over there, but if you follow the way that I drew it, let's go through it one more time over here, coming in on this side over here, going through the armature, and then going down through that diverter rheostat and back out like that, you see that it is once again going to go and be a complete path that we have. So we can, instead of sending all of our current out to the series field, we can go and divert some through that diverter rheostat. That's literally what the name of diverter rheostat means. Last of all, I see that I've got my shunt field. My shunt field just taps off of the generated value of voltage, and we go through here and through here. So we are going to go and have a shunt field, we're going to go and have a series field, and then we've got this diverter that is going to go and be in place as well. We can re-represent this thing the exact same way. If I were to go and draw it out, I'll start with my armature, like that. From my armature, I see that I'm going to go out to a series field. Okay, I'm just going to put an S up top there. And then I'm going to go out of my generator to my load. That's the very first path that we took a look at. like that. We see that I'm going to have across my armature, we are going to go and have a shunt field that is going to be controlled by my control or my field rheostat. So my field rheostat is going to go across there, and then I'm going to go and have my shunt one over there. I guess I'll call this one series because both of them start with a S. And then last of all, we see that we have got that diverter rheostat over here. And what that diverter rheostat does is that diverter is just going to go and be a tap. I could draw it across from here, but it's easier if I just go and take it and draw it over here. Still the same connection. What it is it's going to go and allow us to go and bypass some of that current instead of it going through that series winding. It's going to allow us to go and bypass some of it to go and get out of here. We're going to go through the in-depth, where the flux is and all the other stuff later on when we start to go and look at the actual generation inside of these machines. For now, just know that this is the way that our compound generator is going to go and work. We're going to go and have current delivered out to our load through the series. That's the green path. We're going to have current that is going to be delivered, that's going to be able to go and bypass. That's my blue path that we saw in here through the diverter. And then we're going to go and have the shunt fields that are going around this thing, which are going to just receive their voltage directly off of that generator itself. Okay, let's talk about separately excited fields. Separately excited fields are where all of this voltage that I'm applying for to create electromagnetism happens from the outside of my generator. We're not going to go and see it on our series because it wouldn't make sense for us to be able to go and have it on our series. Where we're going to see it is on the shunt. I know I misspoke earlier inside of there. I was just getting a little bit ahead of myself as I'm working my way through. But just bear with me here. When we have got separately excited can only work with a shunt field. And really what it would be is I would take this shunt field over here. I would go and disconnect over there. And I would go and disconnect. We're just going to disconnect over there. I'll redraw that in a second. And I would go and have a separate DC source that I would go and create. Here up to my DC source. And I'm going to go and have a rheostat that is still going to be my control rheostat in here. It does need to be DC. It cannot be AC. Because if it were AC, it would be changing around its polarity, north, south, north, south, north, south, which would be really bad for what we're trying to do. What we want to go and have is we want to go and have it going through in DC. So we're going to have a negative, positive, like that on my DC source. We'll draw battery because that's the one that we are most familiar with. And we see that this would be what we would at that point call a, I'm going to delete this on the bottom over here because it's no longer a shunt generator. We would call this thing a separately excited. Separately excited one. Taking a look at my current path to my load, I would see that my current path to my load, what my output of my genset does not interface at all with my circuit that I'm going to go and have for my fields. Right? They're completely separated sections over here. Separately excited does go and require you to go and have that separate source, whether it's going to be from batteries or whether it's going to be coming off of another system. It could be rectified off of an AC system, or it could even be a smaller separate generator that is going to go and create that separately excited field. Self-excited is going to be where I'm taking it off of the fields itself, which is what we looked at inside of, inside of the series generator. Series generators will always be self-excited, and inside of my shunt generator, I'm just going to erase all those things I put on here. We'll put this thing back to being a shunt generator. Or if I take a look at my compound is going to be the same thing as well. It's going to be considered to be a self-excited type of generator that we'll have. If I have a self-excited generator, what I do need to have is I need to have enough flux and velocity that I'm actually going to be able to start to go and build up my voltage. Every generator is going to be made out of physical components. We're going to have physical resistance inside of the wire. We're going to go and have physical resistances that are going to go and be at the commutator and the brushes and inside of the fields, etc. So we've got a lot of losses that need to be overcome. And if I don't overcome those losses with a high enough value of voltage, I won't be able to get a high enough value of current. And if I cannot get a high enough value of current, I will not be able to go and get my flux, right? Because ampere turns is going to go and be my flux that I'm going to need out of these things. So we are going to go and have this requirement for voltage buildup that's going to be based around a bunch of physical things inside of there. The number of poles, and I'm reading off the bullet points right now that are on your page, I don't know, 18, 19, whatever it is. Number of poles that I'm going to have are going to be critical because that's going to be the number of windings that I have. The amount of flux per pole, the rotational speed of the armature, how fast it's rotating through the field, the number of paths that my current can go on, lap, wave, frog lathe, all that other stuff, the total number of active conductors that are going to be wound onto that armature, active meaning the ones that are inside of the field at any given moment, etc. All of that stuff is going to be determined by the manufacturer. And what my manufacturer is going to do is my manufacturer is going to go and give this a K. You should be familiar with K meaning a constant at this point. Okay, we've used that inside of a number of different formulas, particularly inside of inductance and capacitance, to go and represent when we have got a K. Remember the dielectric constant that we have when we're dealing with capacitors, etc. So this is going to be a K that's going to be given. I'm also going to go and need to know my phi, which is going to be my flux, which is going to be measured in Webers, and I'm going to need to know my N, which is going to be my rotational speed in RPM. All three of these are going to go and give me my generated value of voltage out of a generator. Now this EG can also be written as EG is equal to BLV. And BLV is really the same thing. L is going to go and be, the length, the active length. In our machines, we call this the K because the K is made up of the L and how many times it's been wound, etc. That's our constant, but it's the same representation. The B, the flux density, is going to be analogous or is similar to what I'm going to go and have here, the flux or the excitation that is going to go and be in Webers. And then the N is going to be my velocity that we're going to have over here. It is another rewriting of the same formula, but it's going to be based around the physical build of that machine. This is a physical one. This is a theoretical one where I'm going to have Teslas, which is flux density, length, and velocity. This one now says, yeah, I've got my length, but I know how I've wound it, etc. I know what my field excitation is in Webers, and because I know my K, I can combine them all together. We're going to go and use these inside of formulas. They give you a formula for one where they say, look, I've got a generator that's running at 900 RPM, so I would just find where I insert RPM. That would be right over here, 900. And it's giving me a generated voltage of 100 volts, so I know what this thing has for an output over there. And it's saying, look, if I go and increase from my 900 up to an 1800 RPM, what's going to happen? Do we know what these values are? No, we could solve for them if we really wanted, but what we're seeing is that we're going from 900 to double 900, which is 18, which would be like 2N that we would have, which means that my volts over here should also go and double. We would end up at a value of 200 volts if we were to go and increase our velocity. So we can change our velocity by increasing the speed that we are going to go and have. Is there anything else that we can go and increase our voltage output with? Absolutely there is, because changing velocity is also going to go and change ripple frequency on this genset. The easier way to go from 100 volts to 200 volts in a lot of cases is for me to go and double the amount of flux that I'm going to have. Remember, flux is a product of ampere turns, which means that really all I need to do is double my amps, 2x my amps, that I'm going to have going through the field. And then I'll be able to go and get the same value of voltage, the doubling of voltage, 200 volts out, but without me having to go and make my engine run any faster. Okay, residual magnetism. Residual magnetism is going to go and be based around this concept called retentivity that you would have learned back in first year electromagnetism. And retentivity is going to go and be basically how well is basically going to go and be how well something holds on to its actual magnetism that we're going to go and apply to it. Once we magnetize something and then we take away that magnetic force, then how well it holds on to that is then going to go and become my retentivity. I want to just show you something real quick. You guys have all talked about this thing in numerous times before. We've talked about this hysteresis curve. And And the hysteresis curve is where when I go and magnetize, I'm going to go and have magnetizing force. That's going to be my plus B, or I'm going to go and have my negative B. This is an AC. And I'm going to go and have plus H, which is going to be residual magnetism, and negative H, residual magnetism in the opposite direction. When we start to go and magnetize something, we're going to go and get this magnetic curve that is going to go and build, and it's going to flatten out. It's going to eventually reach a peak where me increasing the value of magnetic force, the B, is going to not give me any more increase. We're going to have saturated my H over there. And then when I remove my B, so I built this over here, now when I take my B back in the opposite direction, what's going to happen is that I'm going to go and drop, but I'm not going to go and drop necessarily super far. I could go and take my B back down to a value of 0. Once I take it back down to a value of 0, I see that the amount of magnetic lines of flux that I still have inside of here, the retained magnetism, is relatively high. Compared to the peak, it's definitely gone down, but it's going to be relatively high. We would say that that material has got a fairly good retentivity. It's retaining that value very well. We also know that if we would go and start applying the negative B in the opposite direction, we would go and end up with this, where it's going to go and build in the opposite direction, and then it would go back and forth like this. And we go and form what we refer to as our hysteresis curve over here. What we're looking at over here in this graph is we are looking at just one leg of the hysteresis curve over here, where we are taking a look at, they call it now the saturation curve over here. But the saturation curve is just going to be this thing where we are going to go and say, look, as we go and apply the amount of field current, remember that A times T equals phi, flux over here. So this x-axis over here is directly related to my value of field current. As I go and increase my amount of field current, I'm going to go and increase my amount of B, my flux. And what I'm going to go and get is I'm going to go and get flux that's going to go out, and I'm going to go and get more residual magnetism. My generated voltage is going to be coming off of whatever the magnetism is, or the residual magnetism is inside of my circuit. It's going to be directly related to my H value. It's got an H relationship. This one over here has got a B relationship that we're going to have over here. And so the saturation curve follows along with that. Eventually, I would get to a point where I would be saturated, where I'd have the maximum amount of flux lines that I could inside of here, which would mean that my voltage could not rise any greater as well. Remember, EG is equal to BLV over there. So we're going to go and have this, maximum value of voltage. When we hit a maximum value of flux, then we're going to go and have a maximum value of voltage that we're going to go and have out of it as well. So we've got these curves that are going to be interrelated off of here. Now going back to talking about residual magnetism, when I go and shut the generator off, the residual magnetism is going to go and stay inside of the field pole. So we'll just go up to this guy over here, which is my series generator, and we'll say that after I go and shut off the generator, I'm still going to go and have a north. And if I've got a north, I must therefore also have a south over here. And if I've got a south over here, I must also have a north. So when the generator was running, we would have been running current through these windings, which would have meant we would have had a strong north to south that would be going through here. And we'll just draw, two lines to go and represent that this thing was going to be a strong north to south that we had going through here. That's when the generator was running. When the generator shuts down, we're only going to go and have our residual magnetism that's going to be left. So we'll remove that one there. We're going to call this one over here the residual magnetism. Because it is the residual magnetism that's going to be inside of there, when we start rotating this again, so we turn on our prime mover, we start rotating that armature inside of there, we are going to start cutting through a small amount of flux. There's only a little bit of residual magnetism. EG is equal to BLV. We cut through a small, let me just change that V so it looks more V-ish. We cut through a small amount of flux. Because we cut through a small amount of flux, we're only going to get a small amount of voltage. But because I've got that small amount of voltage, it is also going to start to drive a small amount of current. And as I drive a little bit of current through there, remember we've got ampere turns up here. As I drive a bit of current through there, it is going to go and increase the amount of flux, increasing the flux density, increasing the value of voltage, which is then in turn going to go and increase the amount of current that's going out through it, which is going to increase the amount of flux, which is going to go and increase the flux density, which is going to go and increase the voltage, which is going to go and increase the amperage, etc. And we'll continue to go through this building process just really rapidly as this thing starts up. We do need to go and have that residual magnetism on the poles. If we were to go and lose the residual magnetism off the poles, all we would get when we would rotate this would just be rotation. There would be nothing that would go and happen because there is no flux density. If we were to completely lose this and make this a value of 0, if that's gone, we can't get any value of voltage out. If we can't get any value of voltage out, we can't get any amps out, which means that we can't get any ampere turns, which means we get no flux, which means this thing is not going to build any value of voltage. So if I do lose my residual magnetism on a DC genset, what I can do is I can go and disconnect. So I'm just going to quickly do that. I'm going to disconnect this one right over here. And I'm going to go and disconnect this one right over here. And what I can then do is I can go and apply a DC source to it. I don't need to apply it long. Remember that DC sees an inductor as if it were a short circuit. Off of there, I'm going to go and apply a DC source. So I'll get my battery out. Here's my battery, positive, negative, and I want to go and drive my current through in the same direction. So I'm going to go and attach the negative over here, and I'm going to go and attach the positive over here so that my current will flow from the battery through here in the same direction, through here in the same direction, and back out. And I just need to put this on just for a second or two, just long enough that we are going to go and take a bunch of those magnetic domains and re-snap them into orientation. Once I finish that, I just remove this supply, and then I make my connections on my genset again. So we've got it back to connect in series, and then I can start this thing up and run it. If I am going to go and flash a shunt field instead of a series field, that shunt field, what we would have to do is we just disconnect it from the armature, because the armature is considered to be a very low value of resistance, and then we would have way too much current that would be traveling through it. What would happen if I were to go and change my direction of rotation off of these? It does not matter whether we'd be looking at a shunt or at a series generator. If I were to go and change my direction of rotation, I am going to go and build my voltage in the opposite direction. Let's go back to this, the Fleming's left-hand generator rule. Basically, what I would be doing is taking this value that I have over here, my thumb, my thrust, my motion of conductor, and keep that middle finger folded in. I want everybody to make just a left hand like this, just make a left hand finger gun, and then take your left hand finger gun with your thumb up, now flip it so it's upside down, now fold out your center finger. And when you fold out your center finger, you will see that your direction of electron, or your current through there, is going to be in the opposite direction. Changing my direction of current is going to go and cause a problem, because remember, before we had a north to south that was going through like that, looping back around and then going north to south through here, north to south through here. And we saw how we can do that, build a voltage off of here, from our residual. Now what's going to happen is I'm going to be driving my current through in the opposite direction. So I'm going to make a bunch of opposite directions. Okay, I want to use your left-hand rule for coils. That's going to be this one over here. Oh, I just moved that one around. Use that left-hand rule for coils now back on this drawing over here. And if you coil your fingers around from your left hand in the direction of current, those red arrowheads, we see that now my direction of north to south is going to be in the opposite direction. It's going to fight this initial north to south, and it's actually going to go and realign all those little magnetic domains that are going to be inside there. It's going to take them and it's going to go and flip them around so they're all facing the opposite direction. As it does that, it's going to go from having a value of north to south in one direction. It is going to go and have to go and rotate them around. As it rotates them around, it's actually going to go and strip away all of our residual magnetism. Remember talking about that BH graph over there? We've now applied our magnetizing force in the opposite direction, which means that we went and entered this section of the graph over here, where we went and we took away the residual magnetism and we drop it down to a value of 0. What happens when we get to this value of 0 here in the opposite direction? Well, we have no residual magnetism left inside of the genset, which means that the genset is going to now not build up any voltage. We're just going to suck all the residual magnetism off of this thing down to a value of 0, and then because there is no residual magnetism left, Eg is equal to BLV, because we've just dropped this down to a value of 0 over here, we now generate no voltage off of these. It's not usually going to be possible to change any engines around, that like the direction of rotation off of those ones. So usually what's going to go and happen would be that you've connected a field backwards. If you connect a field backwards, it's the exact same thing as if I've got the wrong direction of rotation. If I were to have, disconnected this field and then reconnecting the opposite ends, let's just go and run, this end would have been run over there, and This end would have been run over there. If I were to do that, we would get the exact same thing. Stripping away of our magnetism, and then therefore we're not going to build any values of voltage. Okay, going back to this graph over here, which is my critical field resistance. Critical field resistance is going to go and be a value that I need to go and stay above. Field resistance is going to go and be, based upon the number of turns and, length of wire, gauge of wire, all this other stuff. That's a physical build. What I need to do is I need to make sure that I overcome that with enough volts. So whatever I've got for my field resistance, my volts need to be high enough that it is going to go and give me a value of amps. I is equal to V over top of R. So I need to get a high enough value of voltage that I'm going to go and get a high enough value of amps, which is then going to allow me to go and develop those ampere turns, right? Right below there, I could just use those. These ampere turns, which is going to give me the flux that I'm going to need to go and have. So what we want to do is we want to go and make sure we get the maximum amount of amps that are going to go and flow through my field at the instant of startup. And one of the best ways to do that would be to go and drop my value of resistance, because if I drop my value of resistance, then that means that even the tiny value of voltage that I initially create is going to go and create a fairly large amount of amps. What we'll do is we will go and drop usually this guy right over here, my field rheostat. So initially when I start out, I'm going to go and move this arrow all the way over here on that DC genset, so that most of my current is going to go and take the path of least resistance, which would be around the outside like that over there. And then as this generator starts to go and build voltage, what I can then do is I can start to move this thing back. I'll move it back to the midpoint over here. And now it has to go through a bit of resistance, dropping that value of current. And then if I was still getting too high of a value of voltage, I can move this thing even further down and drop that value of field current even more. When we're starting, we're just going to go and set this rheostat all the way over to a minimum value, and then we're going to let it go and build up from there. Okay, let's talk about prime mover speed off of here. We know that EG is equal to BLV over here, which is going to be my voltage generated is equal to my flux density, my length, and my velocity that we have. We also know that it is also going to be equal to K phi N, which is going to be my material constant, my flux in Webers, and then my rotational speed in RPM over here. It doesn't matter which one of these you want to go and use to analyze this. We see that any increase in a value of speed, velocity or RPM, whichever one you want to look at, is going to result in an increase in value of voltage. Any decreases are going to result in a value of, well, it's going to be a decrease in value of voltage. We don't generally have a lot of control over the speed if we're working off of a internal combustion engine, whether it's gas, diesel, natural gas, whatever it will be. That's usually going to be fixed by the manufacturer. So we're kind of just going to have a range that's going to be inside. Some of our prime movers, we do have the ability to break them a little bit, whether that be wind turbines or water turbines or stuff like that. But a lot of them, we just don't have any way that we can go and handle, what's going to be changing this voltage. We generally will not go and change the prime mover speed a lot. Usually we're going to go and change the field, the flux that we are going to have, because it is seen as being the easiest way. We let our RPMs get up to whatever their full RPM is going to go and be, and we just keep them there at that same value of RPM. Okay, now we're going to get into some heavy stuff. So far we've covered just, some base theory. Now we're going to start talking about this thing called armature reaction. And armature reaction is going to go and be a way that what we're delivering out of our genset is going to go and affect the output value of voltage. So what we've been talking about right now has been everything to do with the fields, the north and the south that we're creating on the outside, and how we adjust those values and where we're getting the current from. Is it going to be separately excited to self-excited? Is it going to be in series, or is it going to be in shunt? All of those things we're dealing with the outside fields. Now we're going to start talking about the actual armature itself. And over here, what we have is we have got an armature that is going to go and have its commutator segments. So I would have this thing broken down into just a bunch of smaller ring segments over here. And then those smaller ring segments are going to go and have connections from, conductor over to conductor. Okay, we're just going to go and take that one as being a conductor across there. We're going to go and take the next one as being a conductor across there. I'm just going to go and take that. That's going to go run all the way through. So I want you to envision that that conductor runs all the way through, around the backside, comes out on that one over there. And then I'm going to go and have same thing for this one, like that. And then I'm going to go and have the same thing for this one, like that, where it's connected to its commutator segments that we're going to have over there. Each of those commutator segments is going to go and have a complete loop. So whatever we have for our armature segments, or for our commutator segments, I'll just draw two commutator segments over here separated from the main shaft. We're going to go and have a loop of wire that's going to go back from one side to the other. And then our shaft goes through the center of that. It's insulated inside of there, runs all the way through the machine. And then we insulate this from the shaft with all that mica, etc. And then we pick up off of these individual commutator sections with our brushes. As we're doing so, we are going to go and see differing values of voltage. I want you to go and use your left-hand rule right now, and I want you to just go and verify the values that we have. First thing I'm going to do is I'm going to go and lay out where's my north pole, where's my south pole. So I'm going to go and have direction of flux that is going to be traveling through from north over to south. So we're just going to do flux like that. Okay. What lines up with flux? Flux is going to be first finger. I want you to place your first finger in the same direction as that flux. Next thing that I'm going to do is I'm going to go and say thrust, which is going to be thumb. Remember, we keep the middle finger for last. Thumb is going to be the thrust, and so I need to take a look at the thrust on the conductor. So if I take a look at my conductors, I see that my conductors, if the rotation is this arrow up top here, the conductors on the left-hand side are seen as going up, and the conductors on the right-hand side are seen as going down. Let's analyze the left-hand side over here first. So we're just going to go and we're not going to cross this center highlighted blue line yet. We will in a minute, but we're going to start with this. Using your finger gun, first finger for flux, your thumb for your thrust, I want you to now fold out your middle finger, and you see that your middle finger shows that the current is pointing directly towards you, which we use off of this dot. You guys should remember the dot and the cross convention. Cross convention means that as the arrow is flying away from you, the dot means that the tip of the arrow is coming towards you. So this makes sense. I want you to now go and take your middle finger, fold it back in, move across now to the other side. Is my field still in the same direction? My flux, first finger still works like that. My thumb, I now need to go and rotate my hand. So you're going to have to flip your hand so that your first finger is pointing in the same direction as the field still, but now your thumb is pointing down towards the bottom of the page over here. And fold out your middle finger, you see that that current is traveling away from you. So this is where we're getting all of these positive negatives off of these. I'm just going to remove all of that because we don't need it here right now. That are going to be off of here. Now what I do want to also take a look at is I want to take a look at this as if it were a coil. Okay, and this is kind of a cool aspect of it. I want you to just go and I'm going to draw over top of here like that. And I know this is not the actual connection inside of here, but we do have current that is coming out of the page on the left-hand side. We have got current that is entering the page on the right-hand side. And I want you to just imagine, just for a second, could this theoretically be a coil? Absolutely could theoretically be a coil. And if I were to go and take this guy and move him from the back, there, maybe actually I won't do that. I'll leave that one in there. But if I were to go and draw this over on the side over here, we'll do the same thing like that. Dot, dot, dot. Cross, 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 like that. I want you to go and use your other left-hand rule, this one over here, that is going to be for your coils. I want you to go and wrap your fingers around that coil that we just made in the direction. Your fingers have to go in the direction of current, and then figure out where the north and the south pole is. So if you imagine that this is a set of coils that we have cut in half right in front of it. Hold on. Stupid glitch. I don't know what happened over there. Back to what we were just talking about, though. If I go back to these ones here, and I'll just really quickly, I was in the middle of trying to draw these, and that all dumped out on me. If we take a look at these as if they were actual conductors going across there, and we've done a cross section of the coil, use your left-hand rule, curl your left-hand fingers around so that your fingers are kind of curling around the back of this coil like that, and they're coming back up towards your hand, and you should see that your thumb is pointing down, which means that there is a north pole that is going to be down here. In other words, as I deliver current out of this gen set over here, I am going to go and create on the armature itself, I'm going to go and create its own north pole. Okay? We see that north pole that is going to be laid down over there. That north pole, if I take a look at it, there's another north pole over here, and this south pole over here has got another south pole over here. And so what we're going to get is we are really going to go and get an extending of our actual poles, which means that my extended pole is going to be, this will be my overall south pole is kind of going to go and look like that. And then this is going to be my overall north pole, which is going to go kind of, let me draw that section, which is going to go and kind of look like that. And if I were to take a look at now where the neutral plane, or the point that is going to be directly halfway between those poles is, I see that that neutral plane has moved off center. I know I've got poor drawings over the top of this, but you should see that this thing is twisting a little bit off center over here. My electrical neutral plane has gone and shifted. Okay, so looking, they've got a bunch of other ones over here that are going to go and show, where we have got norths and souths and stuff like that. They kind of step through a couple of these over here, and they start showing the electrical neutral plane versus the mechanical neutral plane that we are going to go and have over here. What we just drew showed that we had a north pole and we had a south pole that started to go and extend, and we are going to go and have lines of flux that are going to go and change. They're going to go, my north to south are going to go and follow from north to south, and because we've got these like that, we see that those lines are going to go and change inside of there. Two main planes on a machine are going to go and be my electrical neutral plane and my mechanical neutral plane. Mechanical neutral plane is physically based upon the physical build. It's going to be halfway in between these two poles, the physical construction. But my electrical neutral plane is going to go and shift based upon the amount of current that I'm going to go and have going through this. That's going to be this line over here. The more current that I dump through here, the greater the amount of shifting that I am going to go and have inside of here. The more that I go and drive current out, the bigger this south and this north is going to be. So the more that this thing is going to go and twist over, the smaller the current, the less that it's going to be. So it's going to be this dynamic thing. Now I know that they're showing main field distortion on this one over here that is going to go and be in the wrong direction. Okay, this is not the main field distortion that we would have for a generator. This is the main field distortion that we would have for a motor. We'll cover that later on when we go into the motors. So just for now, don't worry about the fact that they're showing that electrical neutral plane translating over there. For my for my generator neutral plane, we saw that it twisted back in the opposite direction. And this is one of the big things about a DC machine, is that where the electrical neutral plane is going to depend on whether it is going to be a genset or whether it is going to go and be a motor, and it's going to depend upon the amount of current. As a result of that, what we want to do is we want to be able to adjust our machine. We've talked about the commutator and the brushes that are going to be on any sort of a machine. What we want to be able to do is we want to actually physically shift where that commutator and brushes themselves actually are. If my electrical neutral plane was over here, I would want to go and rotate my brushes from where they would have originally been over there. I want to go and align them with where my electrical point is here. I'm going to go and have just less sparking and damage that's going to go and happen, because when I'm off of my electrical neutral plane, I'm going to go and have fields that are collapsing. On my neutral plane, I'm going to go and have a value of zero amps that I'm going to go and have. If you take a look at this here in the background, why don't I just erase a bunch of this? You see that right over here, this one has got no current, this one has got no current. So as I would be crossing that, I would not have any current traveling through those components. So we need to be able to go and shift these. You would see these on machines, where you would be able to go and move this thing. Here, I'll draw this for my red one, where I would be able to go and move these around, my actual brush holders, as a complete unit to go and adjust what's going to be on here. It's a bit of a pain because unless I know exactly what my load is, I don't know where to place it. If I've always got the exact same load on my generators, then I'm going to be fine. I can go and adjust it once the first time that I start this thing up, and then we're not going to go and see anything like that. But after that, if my load changes, I'm going to have to go and readjust. Leads to too much fooling around. So what we try to do instead is we are going to go and create a countering direction that we are going to go and have. This countering direction would be us using something that is going to be called interpoles. And interpoles are these cool little things where I've got now my north to south, which was my main north to south that I had going through here. Then I'm going to go and have, it's the same generator that we had off of this one here. I'm going to go and have my north to south that I had created off of here. Right? We created the south on the, Just had to go back there to make sure. I thought I'd drawn something wrong before, but never mind, we're good to go. We've got the south that is going to be created up top over here. We've got the north that is going to be created down here for my actual armature that I have for these. And so what I'm going to do then is I want to go and fight that south and that north, because these are the ones that are coming off of my armature. Okay, well, I'm just going to draw these things as if they were drawn onto the armature itself. So that north down over here. How do we fight a magnetic pole? Well, we go and drive current in the opposite direction. So if I am taking current off of this thing in this direction, traveling out, I would be able to go and stick current arrows around there. It's going to go out through my load, come back in on this side, travel in through here, travel in through here. And I want you to just go and take your left-hand rule and go and create a pole around this. So wrap your finger in the direction of rotation around there. As you wrap it in the direction of rotation, you're going to go and see that we have got a north over here. We are going to go and have a south over here on that pole. Same as this one over here, we're going to go and have a north over here. We're going to have a south over here on that. Now in this case, when you take a look at it, you say, what is this thing even actually doing? Because we saw that before, just based off our rotation, off of this one over here, we saw that we created a south up there. We created a north down over here, just off of my armature field flux that I had over there. Looking at this over here, they're showing that now we're creating another south over here and another north down over here. The reason for this is because the module has the wrong picture inside of here. What they should have is they should have their interpole wound in the opposite direction. This interpole that they're showing over here is an interpole for a motor. For a generator, what we need to have out of it is we would need to have a north over here fighting that. And so we've gone through this thing as it shows inside of the book here. Let's just go and make a quick correction to it. My correction to this would be that I'll leave those ones in there and I'll leave those ones in there. I would just have to go and have my interpole wound in the opposite direction around here. So what I'm going to do is I'm just going to go and take these windings, unwrap those, we'll unwrap those as well. Sure. We're going to go and take that and we're going to go and wind this thing around now in the opposite direction, which would mean instead of me going around like that, I'm going to go around like this in the opposite direction. So this thing here is going to go behind here, and then it's going to come across and through and across and through like that, which would mean that if I'm driving my current out in this same direction now, like that and like that, stick your hand onto there. Oops, sorry, I did that one still backwards. Do that one more time. I need to go and drive it through in the opposite direction because right now we had current that was traveling through in that direction. What I need to do is I need to put it into the opposite direction, which means I need to go and wind my windings in the opposite direction. So we will, I hate the way that it keeps jumping into the front of this one, but not much we can do about it. We'll try this here again. We're going to go behind the pole and across, and behind the pole, and then across like that. As we do that, we are then going to be able to go and create current in the opposite direction over here. Use your left-hand rule now on these currents that I've drawn, and you should see that what we would be creating would be a north over here. What is that north going to do? Well, that north is going to go and fight this south over here. So it's going to start pushing that south back over here in this direction. So we are going to go and have another north over here. This north and this south, in effect, are going to go and cancel each other out. Same with on this one over here, we would have had to rewind that one, so we'd have a south here. This north and this south would also go and cancel each other out. And because ultimately I see the amount of armature reaction, it's dependent upon the amount of armature current going through here, I've got the same value of armature current going through these interpoles, which means that its amount of magnetic flux, ampere turns, is going to be proportional as well. So as this delivers more current and gets more, janky, starts to go and shift the electrical plane, this is going to go and have the same current through it, which is then going to go and compensate in the same direction. It's going to go and cancel this thing out. We do have polarity for generators. My interpole polarity has to be the same as the main pole that is directly ahead of it in the direction of rotation. This comes straight out of your binder, even though they have the wrong diagram that they are going to go and use for it. So what is required is going to go and be that this interpole would be a north, this interpole here would be a south. That way, once again, it has the same polarity as the one that's directly in front of it so that it can counteract the south and the north that are created on the actual armature itself. They're going to go and be fairly thick ones, gauges of wire, because they are going to be carrying all of our low current through them. Usually they're going to be connected inside by the manufacturer. The manufacturer is going to go and take those windings that come off the brushes, they're going to wrap them around the interpoles themselves, and then they're going to go and deliver these things out. Compensating windings is another way that we can deal with armature reaction, and that would be for me to go and have small conductors that are then going to get placed inside of my main field poles. Over here we see that I have got my armature. I see I've got my mechanical neutral plane in the top over there. I see that my electrical neutral plane is going to go and be at this point. We're going to go and have follow your currents through. You'd see that you'd have a north down here and a south down here from my armature, which would combine with whatever north I have here and south I have here to go and shift. That would become my north pole. This would go and become my south pole, right? This would go and shift so that we would have a weird electrical neutral plane. We don't want to have the weird electrical neutral plane, so we are going to go and put in these compensating windings. They're going to be cut into the face, and they're going to be connected in line with the armature. And really what they're going to do is they are going to go and give us an opposite direction. If you wind your fingers around just these coils over here, okay, and we're just going to highlight, going across from here to here, that to that, going across from here to here, going across from here to here. If you were to go and wind your fingers around that using the left-hand rule once again, you would see that this yellow set of windings that I have would give me a north up here and a south down here. And if you compare that to what I'm getting off of my actual armature, my armature is going to go and have a north here and a south here, which means that once again, these two are going to go and cancel each other's fluxes back out. It's important that they're going to cancel each other's fluxes back out equally, and so in order to make sure that there's an equal amount of flux cancellation, what we have to do is we have to run all the armature current through them, so that as this field inside of here, the red fields, the armature field gets stronger, so will this outside one, the compensating field, is also going to go and get stronger. They're going to be less common, and they're usually going to be on, very important type of machines, not on a small little DC genset, but if you've got something that is used for critical systems and where people are willing to go and pay for it, they're going to want to place those ones onto it. Okay, last thing that we're going to talk about is going to be losses. Any loss is going to be created in the value of heat, and it's either going to be heat directly on the generator or on the bearings or on the windings or in the surrounding area, or it could even be remote from it if it's going to be a radiation loss. We're going to have three main classes: mechanical, electrical, and magnetic losses. Mechanicals are going to be called rotational, so it's going to be frictions that we're going to go and have. Bearings are good, but bearings still do have some friction inside of them. Movement of air, the actual pushing against of air, is going to go and slow it down as well. That's going to go and be referred to as our windage losses. And then electrical losses are going to just be resistances inside of our conductors that we are going to go and have. So we are going to, I squared R, watts that we're going to lose off of the actual windings themselves. And then last of all, we are going to go and have core losses or shred losses. Skin effect, hysteresis, eddy current, and dielectric are going to be the bulk of our core losses. We're going to have hysteresis. We're going to have radiation, eddy current, and dielectric losses that we're going to see in there. Skin effect should actually go up into my electrical losses category, but overall it's going to be a lot of different types of losses. Most of these losses as well are only going to be apparent when it's running. Any of my shred losses do not have any way to be measured when I've got a generator sitting still. I actually have to start running that genset up to be able to go and see if I've got the actual losses inside of them. What I will have to do is I will have to calculate my efficiency. And efficiency of a generator is just going to be the amount of power out that I'm going to go and have compared to the amount of input power. Okay? Every generator needs to have power in. We're going to go and say that this is from an engine. Let's go with an internal combustion engine over here. My engine is going to go and have to put power in. Engines are rated in horsepower. But I'm only going to go and get a certain amount of power out, because that power out is going to be limited by what happens in the middle here, which is going to be my losses. Power out will always be less than my power in. Power out will be my electrical power. So what I can do is I can go and give this thing an efficiency, and efficiency is really going to go and be my power out, P out, divided by my power in. And that's going to go and give me my efficiency. They give you an example that, if I've got a prime mover that's delivering 125 kilowatts to the shaft, that's going to be my input, 125. But if I'm only getting 100 kilowatts on my actual electrical generator on the output over there, I'm going to have an efficiency of 80%, 100 divided by 125. All right, that is one beefy DC section over here. It's over an hour long, this video. It's probably going to be an hour and a half by the time that you finish watching, pausing, etc. But it is critical that you go through this video, you understand what's happening inside of it before we can start describing our actual series and our shunt connections that we are going to go and have in our next module, or in our next learning task.